a little bit more the idea that we have these two sessions where I did a lot of theory, and today should be more relaxed, and we could in fact also stop at any point and discuss something in more detail. So as you will notice, also the first two lectures were quite organized. The third one is less so, and I will use the opportunity to actually point out a few things that I found useful over the path of my own work, and this is concerning often also your own relation towards theory and applications, and on that path. And if you go into the business, you will basically also see, you will time and again come across papers where you read the paper and you will think, well, I don't believe that the perspective that is taken is already correct. So that sometimes notions are used in a way that where you think, doubtful. And so these are not directly scientific mistakes. So you set up your system, but where you think that how certain notions are working in the mind of people are sometimes difficult. And to these notions belong, for instance, notions like ecological niches, like fitness, like utility, which very often are interpreted as being a property of the object itself, while it usually is not. And that is why we will also discuss a little bit this notion of fallacies, which is basically have been discussed, I think, in the scientific context, actually since the old Greeks, actually. So you will find such critique already partly with Aristotle. But they come again and again, and why? Because people again and again make the same mistakes in using their brains, and that's why we in the beginning I would like to talk a little bit about fallacies and the guys who talked about fallacies, and then we will look a little bit into what I very recently found to become more and more important for understanding complex systems, basically, and then in the end I will briefly discuss connections to applications, and I will also talk a little bit about how one could approach a quantitative theory of ecology. And I will not show a lot of pictures there, but I will, because I hope that the paper is published already, but it is not. So I will have to postpone your curiosity for these images to a little later. So it probably will archive next week or 2 weeks. However, I can still tell you the story, and the story is, I think, quite easy to understand, and also because I can tell it to you in the context of a already existing theory of macroecology, which is actually called the maximum entropy theory of ecology by John Hart, which has proven actually quite successful, even though it was always the question, why does it work? And we will come to that in the end of this thing. So let's start maybe again with what a slide that I already have shown in the beginning. So what Boltzmann was saying about his work on statistical physics, and then it led him to say these two things. So nowhere else but in science, it is less true that the shortest path from A to B is the straight line, and this is really quite a common experience. I can attest to that. So even in my own work on entropy, I had a moment 10 years ago where I could have made a shortcut to where I am now. But in order to proceed according to good scientific practice and build everything step by step and not just follow directly your intuition, we took a detour that took us 10 years basically. And on the other hand, one way through making such detours understand things much better, or in a deeper or broader way, but also maybe not. So I also could have lived with with the shortcut. So that's why sometimes one has the feeling that whenever at the end one really understands something, that one actually has begun by settling the horse from the wrong side. Good. But this is so why we can come to the following question. So you always can ask questions, of course. So that's, I think, one thing about science that is a nice thing. There's one stream of the science of science where which explicitly is saying that. So there's actually no limit. There should be no limit, or there's no scientific method which would pre-select a good question. So if you believe that whatever esoteric idea you might have in mind is possible, you can of course do that. There's no limit to what you can assume. The limits only come once you want to prove it. So you could, for instance, think levitation is possible and you can try it all your life. But if you don't succeed, you will have to live with your findings. But there are actually not really limits on your initial standpoint. The only thing is, can you defend it? And that's the second thing. So there's one point about this. You can always ask questions, and very often you find out in the course of time that you did not really understand what you were asking. So a lot of the scientific process often consists in actually understanding the questions that you are asking and whether those questions make sense in the way you are asking them, and which kind of answers you might expect on the way. One question one could ask, for instance, is whether, so lately, for instance, in cosmology, there's this buzzword around, everything might be information. And then you, of course, have to ask, what would such a assumption mean? What would it practically mean that you say everything is information? And then you could ask yourself another question. If you believe, for instance, that we basically assume at the moment that our universe is finite, so the current estimates about the number of protons in our universe is about 10 to the power 80, I think. So actually, you don't need space. You just need distances between a finite number of particles. And so each of these particles would have to carry some information about distance. So basically, particles could communicate in terms of objects that are space-like without a continuous space needing to exist. Actually, these questions are not that new because in the 70s there was a huge, for instance, a brief time where so-called non-standard analysis was quite popular. And why? Because it was one was able to show a few things about systems far away from equilibrium that could be computed in using non-standard analysis at the time, and not yet in with usual analysis. And then it just took a few years for measure theory, standard measure theory to catch up, and then non-standard analysis completely vanished again. The difference was that non-standard analysis has a different topology on the real numbers, which means you have notions of infinitesimally small numbers. You have notions about infinitely large numbers. You can divide and multiply all those things, and simply because you have a different topology on your line, and there's of course nothing that would suggest to us a priori which kind of topology does this space have. And in fact, we could ask the question: is space now really an observable object, a really observable reality, or is it just a cognitive construct, which is so suggestive because our brain interprets the world in these 3 dimensions and 3+1 dimensions. Well, but maybe also elementary particles too. So that's that. So a question well posed, and can we decide them? So that's the 2 things. And the decidability issue, I think, is one that becomes more and more important. For instance, the question whether the universe is at its basis algorithmic or geometric is in fact actually a question that cannot be decided, because these both positions are equivalent and can be transformed into one another using a isomorphism. This isomorphism may not be completely obvious from the beginning, and that's another thing. That you could have 2 languages talking about exactly the same thing, but the languages are so different that you don't recognize this in the beginning, and it may take you years to find out. And one example is, for instance, you could write programs in C or C++, and you could write the same programs, or the programs that do the same thing in, for instance, Lisp. And these programs, if you read them, are so different that it will really take you a time to understand that those programs would do the same thing. And this is something that we also should keep in mind.
How is geometric or algorithmic defined? What do you mean when you say this?
Algorithmic, I mean, you have really a number of bits and you do computation. So you have and ors and negations and stuff like that. Or any equivalent. Turing, we will come to that immediately. So there's this notion of Turing equivalence. And then you could have architectures that compute. But for instance, also the game of life, which is one automaton that was popular and studied in the 80s, basically, is known to be Turing equivalent. So you can find initial conditions for the automaton such that you actually can emulate a computer. And then you can use the automaton to do computations and so forth. And so very often it turns out that at some point it is. So the theory often takes us at the nose and lets us believe that a certain phenomenology has certain fundamental properties, but if we look at this type of isomorphisms that you can translate it actually into another language, then these things are often less obvious. And in fact, it was unfortunately I wanted to find this again. So at some point I was googling. About Richard Feynman and his speech he gave for his Nobel laureate speech for the electromagnetic field theory, and I think the 4 minus epsilon expansion it was at that time, and he writes that he had this communication with Wheeler at the time, which was quite proliferative, and that he actually had his theory in 8 different versions, using advancing and retarding I cannot speak today, solutions. So forward and backward running solutions in time, others which just would use fields, others which would not use fields, and basically he could isomorphically translate one into the other. The difference, however, is that each of these theories suggests a different ontology in terms of objects that you accept or do not accept to be real. But since all of them are isomorphic to the point that they all produce the same results for potential observations, simply points out that a lot of things that we may believe to be fundamental properties of the system may not really be that fundamental, or they are fundamental but they are not unique. So you may have, for instance, which is very often happening in mathematics, that you can formulate an axiom system with one set of axioms and then show that this set of axioms is actually one-to-one can be translated into another set of axioms, so that if you use this set of axioms, you can prove a few of those, and vice versa, so that actually you can have different set of axioms which are equivalent. But each time you set such a set of axioms, you are actually in your mind doing something like specifying what the fundamental objects of thought in your case are. And one should probably keep in mind that those need not be unique. So you could assemble different sets that work. And so if you meet somebody who talks about the same thing and uses a different set, then one should avoid to quarrel from the very beginning, because even though you might seem to disagree, you may probably not. And that one should take a little time to find out. Okay. So with this comes along questions like very often you hear, at least read in the newspapers, some nonsense like the scientific method. There is nothing like the scientific method, at least not in singular. So people who try to reduce the scientific method to pure empiricism, I think are failing to see that science is in itself a quite complex process, and with empiricism alone, I don't say we don't need empiricism, it's a very important ingredient to science, but it's definitely not the only one, because it only matters to analysis. It doesn't matter, or not directly matter, to the synthesis. You need the synthetic part. You need to construct your reality out of your observations, and there's no empirical guideline to that. So you can make observations, and then you have to do something with that. And what you do and how you do, and how you work with your observations is of course not determined by empiricism. So there are different rules at work, and they are as much part of a scientific method as any other. So you wouldn't get anywhere, for instance, also if you just would apply empiricism and do not use reductionism. Your models all would be much too complicated. You cannot do one-to-one mapping of the world. That's simply not possible. So there are a lot of. I think to think about the scientific method in singular is a monster and should be avoided at all costs. Okay. So we see this kind of, we are now really coming to the fallacies, and why, for instance, this image of Magritte at his time was so revolutionary, is that the difference between what we see or what we perceive and what really is quite remarkable. So that is one of the most common mistakes. So which is here called the map territory relation, and has been phrased again and again in different ways. And this is not a pipe. This is the image of a pipe. And of course, when you look at it and you ask, is this a pipe? Okay, yes, it is a pipe. And with that comes the problem that actually already, when you say something like, I can see it, I can touch it, I can get the image of it, that you never see reality, you never touch reality. What you do is you see and smell and touch what your brain reconstructs of reality. And that these things are not always accurate is also known very well by psychologists. So you are already working with a map, and that map is the map that your brain produces of the world. The real reality always remains shrouded. You never have direct access to it. So that's one thing that I think one might keep in mind, and which is probably the source of all the other fallacies we will now briefly get along. So remembering that the territory and the map are different things. On the other hand, one has to say, and that has been also said again and again, a one-to-one map would also be completely useless to us. So if you think about a roadmap, and you would want to have a one-to-one roadmap of the Netherlands, you probably wouldn't even get your map into the car. You couldn't use it. So you have to live. So in order to make your theories useful, they need to be reductionist. You need to have a reductionist level, or typically you have to. And that this is possible very often, even for very high dimensional processes, has been lately more or less become clear. There is, for instance, one study I've heard of in the last year, because there was a nice talk at the Hub where people were investigating C. elegans. They were recording the behavior of C. elegans. I think the model, so the recording model in all had, I don't know how many, huge dimensions. But in the fact, if you apply the dimensional reduction method, you actually see that in the end there are something between 7 and 12 dimensions in your feature space for the C elegans. Yeah.
Who gave this talk?
I can look it up. I don't know it by heart now, but
I think my master's thesis supervisor, Greg Stevens, he did this.
it could be. It could be.
Yeah.
It could be. It was very. It was fun. It was a fantastic talk, and
Yeah, he's a good speaker.
yeah, but yeah, and so this was the elegance, but also neural models from optoelectronic measurements of neural activity show similar things. So very often you can reduce high dimensional problems to relatively low dimensional ones. And that is, I cannot prove it, but I'm suspecting it that the concentration of measure phenomenon again has some word to say in that, because I was saying this, one of these measure concentration phenomena is if you're throwing balls into, if you're throwing points into a hypersphere, then they all concentrate actually at the next, at the hypersurface of the hypersphere as n goes to infinity. So if you have very high dimensional spaces, you probably find solutions at the concentrated around much lower dimensional structures. Then it comes also actually I think one should distinguish between theorems and methods, because theorems or hypotheses you can of course prove or disprove. With methods, this is less true. Methods either work or they don't, and even that is too crudely put, because some methods work for some people and not for others. And the only thing about methods is you don't have to believe in methods, just as methods are useful to you or they are not. And in this sense, for instance, yoga is a method. You don't have to believe in yoga. It works for you or it doesn't. And then you either do it or you don't. And in the same way, you can apply methods of measurement, and they either work or they don't work, or anything in between. And then you have to decide whether you can live with the amount of error that your measurements produce, or you cannot. So there's a few things that one, at least maybe it's also just a sign of age. So once you progress and had some years of in the whole thing. So this is why I said I would point out the most anarchic approach to the science of science was by Paul Weierabend. So he had his, I think, most famous work was against method, and again one often sees that people did not actually read Weierabend, because they said, he was really against all scientific methodology there. But what he really is saying is that your primary assumptions should be free, and that is what he was saying here. Basically, is that if you have the difference between a madman and a deep thinker cannot be pinpointed by the positions they take, because the positions could or could not be valid, but only to the amount of rigor these people take in the a posteriori to verify or to clarify their position. So of course, if you are a good scientist and you have a problem and you start collecting the hypotheses you could formulate to a particular problem, then this does not mean that you cannot have a hypothesis that you a priori like best, but it does not mean that a posteriori your liking will be satisfied, because it can turn out that the hypothesis of your liking passes the most tests, but it also could be that the hypothesis of your liking fails and you have to abandon it. And so that is that. So I think Paul Feyerabend was a very interesting person. And in particular, I actually did not very deeply study his, but the philosophy of nature is a really a treat to read. It's but it stops actually before we. He never had time to finish it. So basically, he starts in the old ages, and more or less comes to the Middle Ages, and to the transition to the Middle Ages, and there it stops. But that's really a good read. I could recommend. So then, where things also get interesting again is then actually the scholastic time of the Middle Ages, where the first language critique actually has been formulated by William from Ockham, who basically got fed up by his peers, who were constantly actually falling into the traps that we said before. They supposing that words really have meaning. And that is, of course, not in that sense true. You have to give meaning to the words, and this meaning has to be constructed and clarified. To a priori believe that any word has any meaning is a problem, because it allows you to project your own preconceptions of what you believe to be true onto the world, and that means that you, from the beginning, look at the world with quite distorted goggles, and that is something one, of course, tries to avoid. And what it boils down to was that he was saying that actually a problem that reappears quite recently. There's a fantastic book also that recently appeared, Every Living Thing, which actually describes the different approaches to the origins of biological thinking that were done by Linnaeus and the Swedish guy and the French guy named Buffon, who was actually already pre-inventing evolutionary theory. So basically, Mendel and later then Wallace and Darwin were actually able to formulate the theory of evolution. Goes back to Buffon, and it goes back really to his if they were aware of the language critique, then Buffon did everything right and Linnaeus did a lot of things quite wrong. So basically invent races that do not exist. So he came along, for instance, with these notions that Chinese are yellow, Indians are red, and blacks are black and whites are white. While up to this time, actually, there was no connection made between your racial word race was not even really used between racial identity and skin color. That was simply not present. That was an invention of the time, and a very harmful one that somehow invests our brains up to today. And what Buffon was saying at that time is exactly what Ockham was saying there. Universals are only objects of our mind, whenever we talk about something, we cannot do anything else but to talk about universal things, because we have to abstract. If we talk about human beings, we already have an abstract concept of human beings in our mind. It's not a concrete thing, but every individual we might physically address, so every real thing is individual. So there's nothing general about any particular thing, and this kind of language critique, if one really goes into it, which has been called nominalism, is really a good cure against naive realism, because I'm not against realism in general, but if you do realism, then it has to be what has been called hypothetical realism. So you just hypothetically assume something to be true, and then you verify or falsify it to the extent that this is possible. But this is again actually quite near to what nominalism is, and it's definitely a cure against idealism, meaning that you may have an idea about how the world should be, that is superseding your ability to see how the world is, which is actually not really possible anyway, to a point. Of course, you can see it to a point how it is. But idealism is something that I think one should really try to get out of one's head. Idealism in the philosophical sense, not in the private sense, how people most usually use it. So Occam also, there's this rule of parsimony that has been actually assigned to Occam, but actually Occam never formulated it. So what saying is that if you can explain something with less, that you should use less assumptions to explain something if you can. So that has been actually named Occam's razor, but Occam did not invent it. Occam only used it very explicitly and frequently, but actually it goes already back. You can find it in Aristotle's work, you can find it with Ptolemy, and you can find it already 50 years before Wilhelm of Occam with Thomas of Aquin, which simply states that if you can do with fewer principles, then please do. So then, if we want to have a brief critique of realism, then one could also go to William Feller, who was, I think, one of the great probability theorists of the last century, and which is true for, and he states here something that is true for a lot of mathematical theories. So if people say things like a vector is something that transforms like a vector, then this is exactly what is stated here. We are actually we do not know, or we need not know what a vector, a straight line, a point, a probability, or what else is, as long as we know the rules that connect them. So basically, that's all we know. We know the rules that connect them. But it's very similar with humans too. I don't really know who you are. I don't even really know who I am, but I know how I relate to the world, and in that sense, the relations and the possibilities of action is what defines the rules of the game, and I don't need to know what I'm really am. This really is something we are actually, I don't think we can access. Very similarly, we can, like the question, is now the world really geometric, or is it really algorithmic? I can translate one into the other. I don't need to pinpoint it because it's usually undecidable and mostly irrelevant to ask about the real nature of things. Another thing that I would like to point out where such mind projection fallacies manifest a lot, and one of the theories, one of the disciplines where I think it vestas very strongly is maybe the theory of economy, is that it is known. So if you go, for instance, to small is beautiful by I don't know. So when in the 17th century, in the 19th century, economy became part of the university faculties, which was not always, which was at that time actually not really. So the other faculties were not really happy because they were actually thinking that economy will dominate the thinking of people sooner or later completely if it is made a part of the academic faculties. It was actually explicitly said by economists of the time, we want to make economy a theory that is as precise as physics. And there's a problem with that. And of course, the problem is that human economy is a complex phenomenon, first of all. And second of all, why was physics of the 19th century so successful? Because you can isolate most of the phenomena that you want to study, at least at that time. One did not try to study things in the wild. One could go to the laboratory and you isolate, let's say you make a thermodynamic experiment, you can isolate your system thermally, you can, I don't know, you can prepare your initial conditions, you have control about the systems. In this case, you can study a system in isolation. This is not possible with complex systems. Most of complex systems cannot be isolated, but they can be signified. And that's a huge difference. I can signify human economy within the larger system, but I cannot isolate it. And that's why, for instance, I think the big mistake or the big problem with the economic theory was always the idea of externalities. This is external to the system. And of course, if we live in a world that is connected, there's nothing that is really external. And that is what we see. So if CO2 emissions have been recognized since 1880, I think, to be a possible cause for global warming. And one say, oh, well, that is external to what we are doing. Then over time, one runs into a problem. And that is exactly one of the real concrete problems with mind projection fallacies. If you believe that what you're saying, that things are external and do not have to do anything with what you're doing. So the difference between being that one can isolate something and signify something is something also that I think one should have in mind. Where this also, for instance, I noticed very recently, maybe interesting to visualize that is that one was very happy once one had fully mapped out, for instance, the neural system of C. elegans with every neuron, every synapse, And C elegans is so interesting because it's so deterministic in its growth. So it's every worm is basically identical almost. And then people were assembling these neural networks in the computer, and they found out, well, the computer models of the neural system really do not perform like real worms. And I think a few months ago, 2 or 3 months ago, a paper appeared that was showing that besides having synapses, these neurons also communicate diffusely with neurotransmitters, which, for instance, is not in the map. So in that case, one found out that the map was not the map of the territory was not accurate enough. So you would have to add something, and then usually you still cannot probably tell, say, whether the system behaves like it should or not. Another thing where it frequently happens, and is only starting to get better, is the communication between physicists and biologists. In particular, if it's about regulatory networks, you will very often see these graphs of positive and negative interactions between genes and so forth. And we had the pleasure to work with a biologist who was trying to map out a basic circuit for how prostate cancer affects the concentration levels of certain proteins and RNA molecules in your system or in our system, and we came up with a network that was, I think, 9 nodes large, so a very small network, and with positive and negative links. And then we actually had no idea how strong, from the cake database, we could get some idea how strong these links might be, and we put some link strength on it. But then we were experimenting and varying these numbers, and even though the system only had nine nodes, it's a non-linear system. Its dimensionality is larger than 3. So you could have already chaotic behavior, but what we found was that the system actually had, I think, I don't remember exactly now, but roughly 40 different attractors. So if you put different numbers on the system, and you use different initial conditions for the concentration, one could find that one and the same system behaves in a multitude of different ways. And some of them you can exclude and say, no, that's definitely not what the physical system is doing. And in that sense, you can infer which initial conditions may be completely useless in this case. You can use it to filter out some of the initial conditions, and then you end up with a few that you say, well, in that range, the system may work. But again, one should keep in mind that the image here suggests that you have a system that works in a particular way, but in fact, it doesn't. In fact, the system, well, it works in a particular way, but it works in many particular ways, context dependently, or initial, in other words, depending very much on the initial condition of the system. And with initial conditions, so my projection fallacy, this is again our friend E.T. Jaynes from the maximum entropy principle, who was actually formulating similar stress about what he observed his colleagues in saying that it's not really a good idea to treat for instance, probabilities like you would treat a mass. Because a probability is not really a property of an object. So for instance, the 1/6 probability is not a property of the die for each side, for each phase to occur, and it is not the property of a coin to be unbiased. It is, so for instance, you could make the experiment. I did do the experiment. Take a coin and you start flipping it, and then try to bias it. And if you train for 2 weeks, you can go from a chance from 50-50 to a chance of maybe 1/3 to 2/3 to simply by timing. So you flip the coin, you let the coin spin for a failed time, and then you catch it out of the air. And if you trained it enough, you will see that you can bias that by training it, you can bias your outcome by 1/3 to one or the other direction quite easily. And especially it is easier if you spin the coin very fast, so that its rotation, its frequency is very well defined. Then you can do it nicely. So being a biased coin is not a property of the coin; it's a property of the whole experiment of the system, and it's a property of the predictor. So it's a relation between the predictor and the predicted. So for instance, you could have a situation where let's say you meet a friend, and the friend has a friend of a friend with him or her, and says, well, I don't know. Do you think that my friend here has a tattoo or not? So the one who knows this person already has information, let's say, has a tattoo on the shoulder, yes, and knows it. So for this person, the prediction is easy and it's deterministic, and you can say what it is. The other person who doesn't know the friend of the friend, for this person, it is a 50-50 probability. It might be true, it might not be true. Do you look like having a tattoo? I don't know. So you would probably make some educated guess, but in this case you are dealing with a probability, while in the other case you are not. So the relation whether something or to the how probable something is not really a property of the object. It's a property of the relation of the object with a predictor. And which is of course also to some extent an underlying the whole Gödel business, because here it's not whether you can predict it, but whether you can decide something, and whether you can decide something in a finite number of steps. Okay, one notion where you have a similar thing is fitness. So when you talk about fitness, people have various ideas in the mind. The biologist idea of fitness is very easy and very simple and very straightforward, and maybe the most honest of all. Simply says how much do you reproduce? How much does a species reproduce under certain circumstances? Again, not a property of the species, but a property of the relation of a species or of individuals belonging to the species. Actually, I should say taxon. I should not say species. Species is a word that one could actually avoid. And taxon simply means that what we name like that, and that is probably more fair to say. So with the mouse, it is, for instance, true that on land, in a particular situation, it may be very fit and it may be very proliferative. But if you throw the mouse into the open ocean, it will drown and not proliferate a lot. And so again, fitness is not a property of any particular individual or species. It is a property of the relation between the individual and its environment. The same is true for utility. Utility is not a property of any object. It's not any object can or cannot be utilized by anybody in some situation. So something may be very useful in one situation and it may not be useful at all, or even counterproductive in another one. So in this case, it's again that some sense of a feedback loop has to form for something to be useful and have a utility. So that I think that the most common cognitive mistakes you will find in the literature again and again and again. Once your eyes are trained to, or at least made aware of what to look for, you will see that these fallacies are omnipresent around you. And the same thing, so actually all these fallacies have different names, but they always churn around the same problem. Here you have it in the context of psychology, where also psychologists in the psychologists of the early last century started to recognize that many psychologists actually project their own ideas of how things might be onto their patients. So if they think the patient is mad, then well, the patient may be mad, but he may also not be mad. And I think the first psychologist who really tried to use a systemic approach to avoid this problem is, and I would like, maybe you have heard him, is Paul Watzlawick. And if you come across him, look up the 5 axioms of communication, and I think that's also a very nice read. So he was the first systemic psychologist who noted that no one is mad alone. You are only mad within a context. Even if you really have I mean, you could of course have a chemical imbalance, but what is typically true is that even what Watzlawick, for instance, noted is that dealing with a schizophrenic patient, that once the schizophrenic patient became better, what happens is that he changes his behavior, and then his surrounding notice that, let's say the mother notice in this case, her son changes her behavior, panics because she's not used to this new behavior, and unconsciously drives her son back into the known behavior that we were actually the whole procedure was set out to repair. So you have self-stabilizing mechanisms that in psychology that may be systemic and be not part of the patient or the phenomenon that you are not directly part of the phenomenon that you are. Actually, when I looked up this one, I was somewhat scared how much Alfred Whitehead looks like Putin, but he was actually the guy that wrote the Principia Mathematica with Russell, and the Principia Mathematica. What was it? What was it? The Principia. I'm actually quite in need of holidays, I think. Okay, good. So, but again, the same thing, fallacy of misplaced concreteness, as he called it, is again very similar to the mind projection fallacy. In this case, is that you simply that you mistake the abstracts with the concrete, which is again what Occam was actually pointing to, that all things that we can think and talk about are universal, but every particular thing we can deal with is actually individual, concrete, and that one should not mix it up. And here, for instance, what I pointed out before becomes quite relevant, that we are actually already living in a virtual reality of our own, with our, in the sense that we have to deal, that we actually never directly deal with reality, but with what our brain reconstructs. And with that, we have finished with the fallacies and come to now to algorithms. I think we have said one or the other word about algorithm, but I think there are two or three things to say about algorithms and why I believe they become algorithmic perspective becomes quite important for understanding complex systems. And there are two reasons. The first one is a computation is a phenomenon that only happens in nonlinear systems. And well, let's begin with that. So that is actually what von Neumann recognized. He recognized that with nonlinear systems you can do computation. And actually, he later pointed out, well, that this inspiration somewhat came from the work from Pitts McCulloch on neurons and these integrated fire architectures, and that to some extent you can of course interpret integrated fire. So you have a neuron and let's say in one case you need you have two input dendrites, and in one case you only need one. So you put your threshold in some realm, in some position where you just, the neuron fires if at least one of the two input neurons are active. In that case, you would have an OR gate, or you could have to put the threshold a little bit somewhere else, and you would have an AND gate. So with AND and ORs are actually something like very simple integrated fire neurons with two different thresholds. And in that sense, and since we can build any computer just using ANDs and ORs, and we also need an inverter, we are actually done. So in this sense, we can already show that that neurons are potentially universally computing. Why? Because they already give us something that is more general than ANDs and ORs. You could have but at least they give us ANDs and ORs too. And since they give us ANDs and ORs, and we can build computers with ANDs and ORs and inverters, and inversion also is possible with neurons. So you could build computers from neurons. Just and this means that neurons can emulate the computer, and vice versa. We could, to some extent, of course, emulate a brain in a computer. We cannot, but this is simply due to mostly time and memory complexity. But in principle, one could. So in that sense, we can see, okay, one can emulate the other, and therefore, in the sense of Turing, they would be equivalent. Now, we've said von Neumann invented computation, or his vector machine, register machine, in analogy to neural systems. But conversely, and because neural systems are nonlinear, so the main part is that these systems need to be nonlinear. And conversely, you can of course say of any nonlinear systems that they to some extent compute. And how could one interpret that? You have now a nonlinear system. Your nonlinear systems is now depending on your initial condition, will end up in one of the many attractors it supports. And if you now think about the attractor as a program that your system can run, then your initial condition actually selects the program. So because whenever your initial condition now falls into one of the basins of attraction of one of the attractors, you basically select the program that the system is running. If you go to a computer, this is exactly what is happening. So you have one system, and depending on the initial condition, depending on what you are loading into your memory, you now will play a shooter game, or you will run a scientific simulation. And this only depends on the plus and minuses you load into the memory of your computer. That you can translate this now into readable form is now simply a matter of having the right compilers or the right interpreters installed on your computer that translate now some readable language into computer code and into executable code. And that being said, you have something like the emergence of language with. So once you're dealing with complex nonlinear systems, you have something like emergence of language with it, in terms of the initial conditions that select one or the other attractor. And this is probably one of the reasons why physicists in the course of the trajectory of their life, as they get older, they all turn linguists, more or less. So sooner or later you get infected with the linguistic bug, simply because you start to see that you cannot avoid context sensitivity and path dependence of your phenomena. Context sensitivity meaning, context sensitivity, for instance, in the sense like a mouse fit on land, not fit in the ocean. So that usually the things that you can say are true or not true depending on the context. So no, actually most so computing systems are nonlinear and out of equilibrium. So you have to plug in your computer to run, yesterday we were discussing that if you perform switches in finite time, so if you perform thermodynamic, if you do something with a system, if you let it run in cycles in finite time, that you always have to pay a price for irreversible energy. And the same is of course true for computation. So if you switch your bits very frequently, you have to pay a price for this switching, which is.
So why does it have to be nonlinear system?
For computation?
Yeah.
because you need a and and something like an and and a or.
Yeah, so is that the claim? You can only make an end. You can only make a complete logic when you have a nonlinear
Yes.
system. Yeah. Is it shown somewhere?
The AND gate is nonlinear.
Why?
Let's make the baker example. You want to bake bread, and for baking bread, you need water and you need flour. Let's say these are the two ingredients. Actually, you need more, but let's assume that are the two ingredients that you need. And if so, you say and I need flour and water. If the relation here were linear, you could, for instance, have no water and say, okay, I can compensate for having no water by using more flour, but that is not really working. Conversely, you could say, I have no flour, I just bake bread with more water. If it were linear, this would work, and it doesn't. So and is really a non-linear combination. I mean, it's first of all discrete, which makes the idea. But typically, end situations are I need this and I need this, and therefore you cannot substitute it with a. In the other case, you basically, to make it linear, you would have to substitute it with an or.
Yeah.
Yeah. But you need the stricter thing too, and without it, you don't get it. But I think the more convincing argument is the attractor argument. You need your system to be nonlinear, or one system to be able to have multiple attractors. You want to be able to run different programs on the same architecture. You don't want to. So if you would have to come with your tool set and change the architecture of your computer each time you want to run a different program, you would probably say after a few days throw this thing away and say very unpractical. And the cool thing about a computer is that it's one architecture, and you can run whatever you want on it, depending on what you write into the initial condition.
So I think I agree. I'm just wondering if somebody did anything rigorous outside of making bread, which is a good example.
I mean, I guess if you go back to what Van Neumann was thinking in the beginning, or if you go back to the original papers of Alan Turing, then you probably will find all this discussed. Typically, that is my experience. If you really want to learn how things work, go back to the people who invented it. Afterwards, things are worked out in more detail and whatnot. But very often also what happens later is that the followers or the students of the original inventors sometimes get the original idea wrong. And so which happens also in statistical physics. So some ideas are simply quite so the interpretation. So when Jaynes, for instance, was inventing Max End, it was a consequence of his ideas. Where later followers of the theory were exchanging the ontological position, making the Max End a fundamental property, which it is not. So one has to be. So that's why it's very good often to go back to the original work to grasp what people were really thinking and why they were thinking this. And then you can go back to later work and see what came from it. Okay, I have to run a little bit with my time. Good. What is also what I would like to point out. So, however, once you have a non-equilibrium system, and once it is not reversible, but like most of the systems like computers, we run it in finite time, so you have irreversible energy components, which, by the way, have nothing to do with what is often referred to as Landauer's principle. Landauer's principle is actually dealing with the following problem. If you have a two-state system and you want to rewrite the bit, so you bring your system, you have to bring it over the potential well that separates your 0 from the 1, and so in order to get it over there, and this, let's say your energy level in temperatures, so you have to raise the energy to be able to bring it over the potential well, and then in order to fix the bit again, you have to dissipate some energy. You have to lower it back into your well to have a well-defined state. So you have then to dissipate the energy that is proportional to kT. This is basically Landauer's principle. This is different because it tells you that the irreversible work times the cycle time is larger than some constant, and that means the faster you compute, so the smaller your cycle time is, the larger your irreversible components will, your irreversible energy will be. And you'll notice it with your computer. If you crank up the computational load because you are computing something, it very quickly gets very hot. And that's exactly that. So you're forcing the system to do some work, and then you create heat. And what comes along with that is that actually for non-equilibrium systems, one can show within the cycling theorems that in a truly non-equilibrium system, detailed balance is always broken. So whenever you read a paper which is dealing with a non-equilibrium phenomenon and it starts with a master equation, you already there should be some alarm clocks ringing, because you then already know that the approach will only be approximately true. Because of course you can have cases where your system is breaking detailed balance, but you could have still approximations. Actually, one can show it that each real non-equilibrium system can be emulated by an equilibrium system, but one has to be careful only if you are interested in the marginal distribution functions. If you are interested in higher order distribution functions or correlations, the ability that you can emulate in some sense, if you're not really emulating this, you have one system that behaves like the non-equilibrium system, one equilibrium system that behaves like the non-equilibrium system to a point, namely with respect to the marginal distribution function, but that is usually not what is interesting about non-equilibrium systems. So whenever you find a paper about non-equilibrium systems that starts with a detailed balance and master equation itself might not be a problem. Detailed balance is, then one should read it with care and see where things might or might not go wrong. Because this broken detailed balance also is responsible that the entropy of such system is much lower. So the entropy of driven systems is much lower than one should expect. So that's basically why during equivalences we talked about this already, and this is a nice exercise actually. So if you assume now that our universe is finite and has 10 to the power 80 protons, and as the current estimates are, then you would, and if you think that now distances do not make sense if your distance gets smaller than the Planck length, then you could measure all distances in the universe in terms of Planck length. So you would have finite distances between all objects in the universe counted with natural numbers, and then one could estimate actually how many bits would you need to store all the relations, all the distance relations between the 10 to the power 80 protons, and in fact, one can do such estimates, and it's surprisingly low actually. So if your computer has maybe now a 64-bit architecture, and if we could build a computer with a bus, this computer of course would be larger than our universe, but the number is not that impressive actually if you think of it. So if you would have a bus with 4 kilobit, meaning 4096 bit, around 4000 bit, then with this bus you could store, if you would have a memory with a bus with an address that is 4 kilobit long, then you could store all these relations. Actually, you could store more, so this 4 kilobit would already suffice to store all the relations in a multiverse of 10 to the power 80 universes. And so in a really huge thing. So finite universes mean that actually all we need is finite mathematics. So which makes life much easier, because you will never, in order to understand natural phenomena, need anything like transfinite induction or so. And when it comes to programs, one also needs to distinguish between two types of programs. And the ones are functions. So if you have your computer, what do you have? You have two types of programs running on your computer. One is the operating system, and the operating system should never halt on its own. If it halts, then without you telling it to halt, then usually something went wrong. So if you're that's typically when your operating system halts, then you would say, oh, it got frozen, then something did not work anymore. On the other hand, you have functions that you can call, that execute, and that then should return again. And I think this distinction is quite interesting to make. And since we now have this analogy between non-equilibrium nonlinear systems and computational systems, where you can identify programs with the attractors of the system, and then you can try to translate notions like error states and recovery states, actually also in non-equilibrium systems. So you could, for instance, say at the moment our planet is operating with an operating system that supports threads that are all the function threads of organisms, which are called, they are born, they execute, and then return, they die. And so that would be a function, and the opposite operating system runs. But if, for instance, now you would have a bug in your program, and you would have some of these functions would start to write information into memory that is actually crucial for the operating system. And if we think of this memory, for instance, as being all these bacteria, these bacterial organisms in the oceans that produce, I think, 60 to 7, or something between 60 and 80% of all the oxygen requirements on this planet. And we were now to write the wrong chemicals in the oceans, and we would kill these bacteria. We would actually go back to a mostly anaerobic existence on this planet, which basically means that the operating system would have to shut down all the threads that are working on oxygen, and the recovery state would be a state where only threads can be run that are again anaerobic, so cyanobacteria and so forth, and the rest would basically be gone. Okay, so these analogies between computation and computational systems and large complex systems can be made, and they are. I mean, to some extent, this is a choice you can make whether you interpret them metaphorically or more concretely. But actually, you can interpret them quite concretely. The feedback loops are, however, a very crucial thing in the whole thing, especially when it comes to human societies. Also, some read that I can. He's an excellent writer, witty writer. Robert K. Merton is, by the way, he was not his original name. I don't remember his original name. It was I think he came from Poland or some of the Eastern European countries and had a respective name. And when he went to America, he was actually financing his studies by being a stage magician. And Robert K. Merton was his stage name. And then he got a fixed faculty position and actually took his stage name as his real name. Very good observer. So there's one book I can, which has little to do with science, but then again not, because it has to do with whether or not we can actually correctly cite the people that have invented something, and that is actually quite difficult, as he showed in this book, On the Shoulders of Giants. So he was tracing the Newton, the sentence that was attributed to Newton, and it's often claimed that it expresses that even Newton had a humble side to him, which I don't believe. But in fact, he traces the notion back much further in time. And that is also something usually true, that very rarely the people who actually invented something get the credit for it. And also that things usually get invented multiple times, and then multiple people get credit for it. But anyway, he's the guy who invented, who came up with these notions of unintended consequences, which is maybe one of the most important things to keep in mind that whenever we plan something and we perform something and we do something with a purpose, that even though we may achieve our purpose, there is always something happening at the sidelines too. So there are always additional consequences which we may not have had on our radar. And one of the famous examples may have been the fluorocarbon usage as a spray doses. So actually, I don't remember the name of the chemist. He invented two awful things. He invented leaded petrol, and actually in the other case, leaded petrol, I cannot redeem him, but in that case, he wanted actually to make safer refrigerators. The earlier refrigerators ran with refrigerants that were based on phosphorus mostly, and were quite poisonous. So if you had a leak, you could really have a poisoning. And he came up with a different substance which was not poisonous, and in this sense, it was a very good idea to replace the refrigerants in the refrigerator with fluorocarbon hydrates. However, fluorocarbon hydrates, because they were seemingly not poisonous, were then used in large quantities in spray doses. And as we all know, they were in the end responsible for the hole in the ozone layer, and one of the few examples where then the world community came together with a ban. It was not 100% ban, but quite a strong limitation on the usage of fluorocarbon hydrates, which now leads slowly to a recovery of the ozone layer. So this would be a example par excellence for an unintended consequence of something that was actually intended to be something positive, which may give the proverb, "The road to hell is paved with good intentions," a quite real meaning. Okay, good. That's also said, so context sensitivity we also discussed already. You could say something in one context, and in this context it could be funny and witty, and if you say it in a different context, it may just be an unpleasant person. Okay, so then let's use the last quarter of an hour. I thought we had an afternoon session, but seemingly we don't. So I can only briefly sketch now what I wanted all to say about ecology, and because I actually wanted to discuss it mostly in the afternoon, but I will now do this in a very compressed way. So in last session, we were talking about power and irreversible work. And there's this one point now, because the faster your system runs, the more irreversible, the more energy you lose for irreversible work. So there's one point, one frequency where your system has a maximum power output. Then you have the spot where your system runs idly, meaning that all the work is used for running the machine, and no external work is performed. It would basically be ecosystem, for instance, Earth as a total thing. If you think of it as a the dynamic machine running between the hot heat bath being the sun and the cold heat bath being the microwave background that has a temperature of about 3 degrees Kelvin. So you work between 6,000 degree sun surface temperature and 3 degree Kelvin. So your efficiency, your Carnot efficiency is almost 100%. It's think 0.9999 and something. And so you can safely assume that all the energy is the whole power is used irreversibly for running our system. And now the question that Lotka asked in the 20s is, they noticed that thermodynamics gives us a means to say mostly what is not possible. So it gives us a limit. It says, okay, heat always goes from the hotter to the colder system and so forth and so forth. But it doesn't really tell us what will happen. And I mean, at Lotka's time, maximum entropy principles had not been fully developed. I mean, of course, there was already Boltzmann and Planck had already used it for dividing the black body spectrum and so forth. But in biology, it was less clear how to use it, and mostly because things in biology, of course, are very complex. And the question was now, the idea from Lotka was basically, okay, if you now have two species, and the one species can use the same amount of energy more efficiently, then the more efficient species will prevail. There's another approach. Well, that is one thing. This gave rise to this idea that one could use maximum power principle. So does the system actually maximize? Oops, let's go back. Maximum power, and as we already indicated, this may be true for a part of the species, mainly multicellular life, probably, and but for single cell life, some will be also here, but some, if the environment is very poor, it may want to be more efficient and would go away from the maximum power solution. However, if the question is now, do they really maximize power, and do species really maximize power? And if I would have and the current answer that I would give from what we've learned recently is not really. So what I can tell you without showing it to you now in detail is what species are actually doing. They are minimizing the amount of power the species invests per fertilized egg. So the question is how much power do you have to invest into your offspring? And what is happening is actually that species, not you in particular, but species in general, are minimizing the effort for producing viable offspring. Depending on some parameters, you of course have to say how big the adult body size of a species. You have to specify the reproductive efficiency. So in the reproductive efficiency, there would, for instance, go in some notions of which would, for instance, explain such differences in if you have simple sea-based creatures at the bottom of the food chain, they would basically produce massive amount of eggs for some of them not to be eaten. While if you go to larger and larger species, they invest more and more energy into their offsprings and to guide them and protect them for a while. some of these things can be really nicely understood. So he's talking about different into energy channels that are favorable for the survival of the species. And what we could see lately, so in our model that unfortunately we have not yet published, there are three main things with which you can explain a multitude of phenomena for taxa, and that is the three main energy investments, actually four. The one is the metabolic baseline. The metabolic baseline is known to grow with the body mass like a power of m to the power 3/4. This grows with m. This is called the metabolic allometric scaling. And here, this has been done extensively by Geoffrey West. I think he started working on this in the mid-80s or mid-1980s, and is still working on it. So he's now past the 80s, but he did a lot of work on metabolic scaling. So the metabolic baseline is something, but the metabolic baseline only is the amount of energy that you minimally require not to die immediately. So this is, if you're usually it's measured with animals. When you measure animals, they are heavily sedated because you need to put them into a calorimeter for a time. And so think of yourself as really resting very deeply and doing nothing. That's what the metabolic baseline is. However, typically species have to invest energy into other things too. So they have to invest into growing. They have to invest into reproduction eventually. And they have to invest into error correction. And error correction is actually a quite important part. There are two reasons why error correction is particularly important. One thing is to say, if you fight the infection, your body can use up to 1/3 of its total energy usage into fighting your infection. So it's really, really an important energy channel. There's a second thing why error correction is quite necessary. So you constantly, radiation is breaking up your DNA strands, and your DNA repair mechanisms have to work. They all need ATP. And to get the idea of how much energy you are using every day, is that your body produces. So at any time, there's about 200 grams of ATP in your body, but your body daily produces your own body mass in ATP. So if that's how much energy you are using. So this is really, there's a lot of things happening, even though we don't see it. That's something that one should keep in mind. So good. There's an early phase in life where error correction is quite necessary. Why? Because at the time when the parents produce the offspring, already a lot of errors have accumulated in your body. So the first thing that your egg cell will want to do is to repair all these errors that they have inherited already from their parents. So in the first phase of your life, error correction you only invest into your bodies only invest into growing and into error correction. And then at some point, and that's actually like a phase transition, so what happens is that the energy usage for growth goes down. Then the energy for, at the same time, the energy investments into error correction go up. Or we even start here already, so they crank up. Then they go down. At that time, the reproductive energy investments into reproduction go up and then go down quickly again. And then error correction also goes up again. So this is basically the phase in life, the reproductive phase in life, where so this is how energy investments typically look like. So in the first time and this has a consequence that in the beginning and actually one can show all this using a maximum power approach. So this is possible. Okay, and how does one do that? Basically, one sets up the demographic equation of how yeah. Scaling and the demographic equation. So what you're doing is you're using the demographic equation. Then you can say something about how the number of species in your system are evolving over time. At least if you use the stationary solution, you can do that. Then you can say something about the death rates, and the death rates become a functional from the depending on the amount of energy that you invest into error correction. So in the background you have a error model. So you start with a number of error. With each cell division, your errors get propagated. The number of errors that can be corrected depends on the amount of energy that you are investing into this. And so you can set up a number of equations actually that allow you to come up with all these solutions. And it also allows you to make if you say you are ignorant about trophic relations between species in an ecosystem, you are actually it's also possible to say that actually power works quite in analogy to the energy in the equilibrium Marx-End principles, and you get something that looks a lot like a Marx-End principle, however, not for the number of individuals of a species, but for the number of eggs produced at any given time. And what comes out actually quite automatically using this model is that you get things that look very much like this Gompertz Meckham laws of death rates. So what you have on the y-axis are death rates, and then on the x-axis you have your life, and you have the age of species. And what you see is that in the beginning, death rates go down, and actually they go down. They have their minimum always here around 10% of the life expectancy. So roughly, yeah.
So death rates are negative? The death rates are negative on that?
This means n out of 1,000 per year. So these are humans. So here you would have one death per 1,000 individuals per year, here you would have 100 deaths per 1,000 individuals.
So on
per
the left,
year.
the numbers are negative.
And here it's simply the exponent. Here this would be 10 to the rate in terms of, I didn't look it up for the Drosophila, but it's probably death per day, I would guess. And then it would be 10 to the minus 5 and 10 to the minus 1.
Yes.
The rate, which all would be smaller than 1. But basically, they all look a little bit alike. First, the death rates go down almost linearly, and then they go up again. And one element that is actually, again, where we again see the staircase a little bit, that is underlying some of this, that's the next stage where we are at the moment, and what we can do, we could incorporate trophic relations into the whole into this whole energy investment business here by considering that typically the predators are usually larger than the prey. With that, we also again would get something like a staircase and can make predictions about how much energy ends up at which trophic levels. But this is still a little bit future work. To come back here, there's already one existing theory, entropy-based theory of macroecology. I was talking about Hardy et al. It works very well, but now we understand why it works very well. The prediction, so you're actually solving the Max-End principles with these two constraints, where you say, okay, n is the number of species you observe, epsilon is the number of individuals with metabolic rate epsilon. And then you say, okay, the first thing is that the total number of species here is on average the total number of individuals of a particular species is the total number of individuals in the ecosystem divided by the number of taxa. Basically, D is, I think, the number of taxa, and that the average energy per taxon is also the total number, the total energy available to the system divided by D. And the predictions that come from this are quite nice, but we start to understand why they work very well. It's much simpler than the theory that we developed. However, we can make some final predictions even for the energy investments. Is that the exponential decay of this would mean, for instance, that the larger the number of species the number of individuals in a taxon with energy with metabolic rate epsilon decay exponentially, which basically reflects the fact that if death rates would be constant in your over the lifetime, the demographic profile would be an exponentially decaying function, and that means that, which is not completely true in reality. They have bumps and whatnot. However, on average, it would be for a system that has evolved, that is left alone and is more or less in a stationary state. It works well because the zero brain, so that the simplest prediction for the demographic profile would be exponentially decaying population with age, and that comes out of the first, the first, the assumption and from the second assumption, this is very close to what we get for X, only that here it happens for. So one could say it works well because it approximates some of the more complicated factors nicely. And with that, I think I should stop here. And again, my team. So this with Hannah, we did all this. Actually, we did some work on cooperative games, cooperative economic games, and now we did this work on this macroecological theory using Max Power with Ray Fuentes. I'm now working on the emergence of ecological niches, which we have no time, but it would be an interesting thing to talk about. He's a biologist who works in the Philippines. From him, I will get reef data soon, and we hope to gauge our eco model. Peter Hitzberg or Minas Mutra. We worked on the staircase and process, and recently on the typicality approach towards entropies. With Markus Hofer, we have in Jan Korbel, we have worked on the generalized entropy business, and Stefan Turner is my long year colleague and boss of the complex system hub in America. Unfortunately, already has died, but it was a good experience to have worked with them. Okay, and with that, I think I will stop. And unfortunately, we have no afternoon session, but maybe if we now still want to drink a tea and you want to ask questions, please do.
Yeah.
Thank you.
First, thank you very much.